Hey everyone, welcome to our second video on volume of solids with no revolution. As I promised in the last video, we are going to do example 2 on the back of the note sheet. So let's get into it. This should go a little bit faster because I've sort of laid the groundwork in the first example of how this all works. So let's just do this problem. It says, find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 9. So that's going to become very important. The base is given by this equation. And then they go in, and whose cross sections cut perpendicular to the x-axis are, and it's the same 3 shapes that we did in example 1. Okay, so what I did first is I took graph paper and I started thinking about the equation of the base, x squared plus y squared equals 9. And we've talked about this several times in this class. This is the standard form equation of a circle, and this circle is centered at the origin with a radius of 3. So this is going to look like this. And I'll do my best to draw a nice, neat circle. So there's my base. So this goes back to, remember these paper clips yesterday? If I turn this over, it's a circular base. Lots of things in the real world have a circular base. Now, the other thing I wanted to do, just because of my work on the last example where I had to do top minus bottom to find like lengths of my square cross sections, the base of my equilateral cross section, or the diameter of my semicircles, I knew I was going to have to figure out like what the top function was and what the bottom function was. Let me get a different color highlighter, because as we know, when we start to solve the equation of a circle for y, it becomes piecewise. So if you take a look here, what I did over here is I moved the x squared to the other side and square rooted. So y ends up equaling plus or minus the square root of 9 minus x squared. So the top here, the yellow, is going to be given by the positive y value, so the positive root of 9 minus x squared. And then the blue is going to be the negative root of 9 minus x squared. So I want to establish right now that the distance from any point up here to any point down here on the blue, this distance is going to be given by the top minus the bottom. If I take the square root of 9 minus x squared minus the negative square root of 9 minus x squared, the double negative adds together, and I get 2 of these root 9 minus x squareds. So I want to establish that I don't care if I'm over here doing a cross section, if I'm tall doing a cross section, or little right over here, wherever I'm doing a cross section as I grow them out of my base, the distance from one side of the circle here to the other is 2 root 9 minus x squared. That is going to make life a lot easier as we work through this problem. So let's take a look at our first cross section. So we start with cross sections that are squares. Now, if you remember from our last example, we start with v equals definite integral. And we have to bound it where the x's are bounded because we're cutting perpendicular to the x-axis. So we're going from negative 3 to positive 3. So let me put that in. In fact, let me do that for every problem that we have. And the other thing I can put on all 3 of these, on the back, I can do dx, dx, dx. And while I'm here, why don't I put the generic formula for a cross section that's a square, a semicircle, and an equilateral triangle? So the area of a square is side times side, or s squared. The area of a semicircle, pi r squared over 2. And the area of an equilateral triangle 1/2 base times height. Now all I have to do is get these guys in terms of x. So the squares are going to be pretty simple because I've already established one side of my square cross section. It's 2 root 9 minus x squared. Well, if I grow out and across and down these square cross sections, well, the height of the square is going to be the same because it's a square. So all I have to do is equals definite integral from -3 to 3 of 2 root 9 minus x squared, so that's one side squared, dx. And if I throw that into my TI, where's my TI? Losing it. Throw that in there, I get math 9. Again, for doing these on the calculator to move this along. If we want to do these by hand, we can do that too. So -3 to 3 of 2 square root 9 minus x squared quantity squared dx. So I'm getting 144. Okay, that was nice. 144 units cubed. Done. Semicircles. Okay, well, I need the radius. Well, picture semicircles growing out of this base. These purple lines here, these purple line segments or chords here are the diameter, aren't they? From top to bottom. I shouldn't say diameter. No, because we're not going necessarily through the center here. So it's not the diameter of the circle, but it is running from the top to the bottom. So it's running the full length of 2 root 9 minus x squared. So when the radius, if this whole thing is the diameter, then the radius is half of that. So if you take 2 root 9 minus x squared and divide by 2, you have your radius, which is the square root of 9 minus x squared. So that's what I'm going to put into my formula. So equals definite integral, -3 to 3, pi square root 9 minus x squared squared over 2 dx. And when I throw that into the TI, what do I get? Math 9, -3 to 3. I'll do a fraction. Pi, parentheses, square root 9 minus x squared over 2 dx. So I'm getting 56.549. 56.549 units cubed for my second one. And last but not least, equilateral triangles. 1/2 base times height. Now again, this is like the Toblerone. Remember him? The base is already established right here. It's still just this length, 2 root 9 minus x squared. And if you grow out the equilateral triangle, all sides are going to be 2 root 9 minus x squared. So what I like to do, we can put that in here a while. So we've got the definite integral from -3 to 3 of 1/2 times 2 root 9 minus x squared. But now I have to find the height. So let me look at one equilateral triangle cross section. Okay, so I know this whole distance is the 2 root 9 minus x squared. So if I want height, I know this little guy right here is just half of that, which is root 9 minus x squared. And I know this side is 2 root 9 minus x squared. Okay, and I'm looking for height. Now I gotta be honest with you guys. I could do the Pythagorean theorem. I could, like we did on the last one. Problem is, on the last one, when we did the Pythagorean theorem, our sides were all constant, so it was pretty simple. When it gets a little uglier, I want you to be able to appeal to special right triangles that you learned about in geometry. There was a rule in geometry that says, when you have a 30, 60, 90 triangle, which is what this is, here's your 90. The angles, the three angles of an equilateral triangle all measure 60. So this is 60, this is 60. This top angle would be 60, but since we split it in half, it's 30. So you now have yourselves on this half a 30, 60, 90 triangle. And there is a rule, and I'm going to come down here. Got to find space. There's a rule on a 30, 60, 90 triangle that says this. Here's the 30, here's the 60. Okay, if the short leg, which is the guy across from the 30, if we call him A, then the hypotenuse is double that, 2A, and the leg across from the 60 is A root 3. This is the relationship that's always true between the sides of a 30, 60, 90 triangle. And if you look over here, check it out. So here's the side across from the 30. It's the square root of 9 minus x squared. That's the A. Now look across the hypotenuse, twice that, 2A. So 2 times the square root of 9 minus x squared. So we can then say that the height is A root 3, which is just the root of 9 minus x squared, root 9 minus x squared times root 3. That's the height, and I didn't have to use the Pythagorean theorem to get it. So that is what I'm going to put here for height. Root 9 minus x squared times root 3. And if I plug all this into my calculator, I should have the correct volume. So let me finish this video with that final calculation. It's going to be Math 9, -3 to 3, 1/2, this gets a little ugly, be careful, times 2 root 9 minus x squared, that's my base, times my height, which is root 9 minus x squared times root 3 dx. And I'm getting 62.354, which is the correct answer, 62.354 units cubed. Final answer. So thanks for watching. This is not the easiest lesson to do via video, but if you were absent or need a little extra help, hopefully this did help you. Okay, thanks for watching.